Okay, that'll record there. Here's a marker here. Are you just gonna use that for the grid?
Yeah,
Okay. Where were you sitting? I'll just sit with yours.
I was over there.
Okay, everybody, and that was command as much respect and your attention right now to do with me speaking, so pay attention.
Okay, so hopefully since you're in this class, you've all taken Calc 1. If you haven't, there's a bigger problem. So in Calc 1, it's blank. Okay. We talked about finding the area of the section with the function f of x bounded on a to b. And so the way we take the area of the sector is going to be we split it up into these smaller sections. And then we find the value of the function on each section. And we add those together. And that's how we find the area. So our equation for that is going to be the area of the sector is equal to the integral from a to b of f of x with respect to x. So that's going to be. Now, the way we're going to translate this to Calc 3, we're going to draw another diagram. And we're going to give ourselves a shape. For this instance, it's going to be this funny rectangle. And this is going to be our z, our y, and our x. So we have our area of a sector. We have this. This is our surface up here. And we're trying to find the volume of this shape. So what we're going to do is we're going to cut it up into slices. And let me see. We're going to take the area of the sector inside each slice. And we're going to do that. C to D. We're going to take the area of each sector with respect to the y-axis from C to D. And so this is going to come out to we're changing this to f of xy instead of just x because this is in the 3D plane, so we have two variables. So this is our formula. Now let me give y'all a quick representation of what this looks like with the area of the sector, the volume of a non-rectangular region. Non-rectangular. So this is our area of a sector. The top of this slice of bread is the function. This is our shape, and we're just going to add each of these up to get our non-rectangular region. So that's how this works. Okay.
So when we pick that sector, we're finding the area that's like, so what's the difference between a slice and kind of close?
Okay. So the slice is just, you're taking this and it's just a chopped up piece of the loaf. Much like with bread.
And so instead of finding the area, you found.
Volume.
Thank you. There it is.
Yes.
And the difference between double regular intervals and your double is going to be you're going from the line into an area. Now we're taking areas into a volume. That's really the only difference. So triple integral is going to now we won't change the spatial dimension, but we're going to now start adding other parameters to describe our three regions instead of only necessarily integrating over a area. Okay. We're going to talk about one more type of way we can describe a region in R2, but this time using polar coordinates. And I'm going to preface the the next week of lectures. Today is polar. On Wednesday, we'll talk about triple integration in terms of rectangular prism type regions. And then we'll talk about these coordinate systems called cylindrical coordinates and spherical coordinates. In other words, you could describe points in three-dimensional spaces with more than just your typical X, Y, and Z. So I like to think about it as having different languages. So you can communicate the same exact ideas, but with different words or through different vocabulary and rules of grammar. And let's see, where did I put it? Oh, there it is. I like polar regions because circles are very, very disgusting in Cartesian. The way that often happens is you start with something like, if I took a circle, and this circular region in R2, if I knew that this had a radius of R and it's centered at the origin, then I could say, okay, I have x squared plus y squared is equal to R squared. Good? Now, the issue is, what if I actually want to describe the bounds of this, right? Now I have to start describing as a function, I have to split this up because by the vertical line test, it fails to be a function. And so what ends up happening is I say, okay, well, y is equal to the plus or minus square root of r squared minus x squared. And now all of a sudden, we're having to deal with these integrals of square roots of constants interacting with quadratics, and then two completely separate parts. You have the positive root and the negative root. And so circular shapes, elliptical shapes, these kinds of rounded out shapes are incredibly clumsy and really, really difficult to talk about in R2, especially with rectangular coordinates. I mean, it's in the name, rectangular coordinate is not going to go well with circular things. And so we're gonna talk about how to describe rounded out regions like ellipses, circles, and things like that in a much more convenient coordinate system. So how we're gonna do this is, it's been a week. Now let's recall the primary thing that we were talking about. We had a rectangular region in our input space XY. And if I take a rectangular region as such, this is A, this is B, this is C, this is D, that is a rectangle. We're looking at a very specific portion of our input space that's underneath the surface that we're integrating underneath. And so the way we would describe this in rectangular coordinates is I say, okay, so here are my points x, comma, y, indicating we're rectangular. And how am I restricting my x? Do you remember? I take A less than equal to x less than equal to b. And along the same lines of reasoning, what do you think it's going to be for the less?
C less equal to x1.
So that is a rectangular way to represent this particular region. And we call this a rectangular region. Potentially, we call it a rectangular region for the reason that, well, the region is a rectangle. And so what we're going to do is when we step into polar, we're going to define something we call a polar rectangle. And so it's going to be a similar kind of motivation as to, we're going to have two variables constrained by two constants. Now, it's not going to look like a rectangle, it'll be a polar rectangle. So it's going to be kind of spun around and rounded out. And let's talk about what that's going to be in polar. So a polar rectangle is going to be described, instead of with x's and y's, what are the variables for polar coordinates? R and theta. So we have our set of r's and thetas like this. And then we can think about how we're actually going to bound this. So the radius is, well, we can't have a negative radius. That's the first thing we need to say. So 0 is, that's the bottom. Nothing's going to be allowed to go under 0 for our radius. And then now we actually need to choose our bounds. So a less than or equal to whatever our radius r is, less than or equal to b. So we've bounded the radius. And now theta is going to be telling us how much we're sweeping around in a top-down view, kind of like watching this spin around. And so that's going to govern we use a Greek letter alpha less than equal to then Greek letter beta. And if somebody tries to convince you it's pronounced beta, that means they don't do Erasmian Koine Greek. Okay. And then there's a semicolon because there is one condition. We don't want to wrap around our alpha to beta. Basically, we don't want to double count that stuff that we've already swept out. And so the way we prevent that from happening is the difference between the furthest extent of our angle to the lowest extent. We just want to make sure that stays underneath the full rotation, because if that stays under a full rotation or it's equal to a full rotation, we preclude the issue of accidentally wiping out more than we're in double counting. That makes sense. So let's actually visualize what's going on. So here is R2. I'm still going to label this as X and Y for reference points because the relationship between Cartesian and polar is simply X is R cosine and Y is R sine. And so here, if I have some sort of, if I choose some sort of an alpha, so this would be like the first angle, theta is equal to whatever alpha is. And then maybe I choose a different theta like this. So I stop at theta is equal to beta. But then now I actually need to talk about how long my R's are. So if I have a region like this, that was actually pretty good. Nice. Here's my region R. Now, what do you think the A is representing here? Which distance on this particular rectangle, polar rectangle? This is A right here. So A is telling us, okay, that's the lowest extent that we're going to start counting out. So the way that polar coordinates work is essentially you always start from the origin. The very first thing you do with the R is that tells you how the distance away from the origin you're going. And then the theta tells you, okay, you want to go a certain distance away from the origin, but then specifically at this angle rotated. And in that way, you can sweep out with the infinite spiral every single point in R2. So this is a valid way to talk about coordinate systems for R2. And then B is going to not be the shorter radius, but it's going to be the further distance away, right? So B is going to represent the further distance away. And so this is how we talk about a polar rectangle. It's a little bit different. Here we're talking about A to B is just being Cartesian and C to D being Cartesian, so we can more easily visualize that. Now we just got to convince ourselves that, okay, when we talk about these A and B for the R's, that's actually giving the distance away from the origin. And then the theta is telling us how much we're sweeping out. Okay, let's do an example of this system. This is kind of the most important part, is being able to visualize in the input space what these are really doing. Because if you can't do this, it's actually really frustrating to try to set up the double integrals. So I'll spend time on this as we need. So for example,
What does theta do?
What?
What does theta do?
good question. Theta is telling you how far you've swept around. So theta is always going to pretty much be bounded between 0 and 2 pi. And when we're looking top down, because there's no need to double count spinning. So that's one nice thing about the polar system, is that you're always going to be guaranteed somewhere between 0 and 2 pi when you're setting up these double integral regions. Okay, and so now let's see if we can, well, more for you. I know I can do it, that's not the point. R theta, and see if you can draw on your own paper for yourself what this polar rectangle looks like. So if you were told that you're going from 0 less than equal to R less than equal to 2, and that 0 is less than equal to theta is less than or equal to 3 pi over 4. Can you actually draw what that region looks like in R2? So everyone take a stab at it while I set my axis up. And as you do it, I'll ask you a series of questions that you can ask yourself as you do these. And I'm going to specifically use the items in the region to help you find out that you can set this up on your own. For the radius, what's the lower bound?
Zero.
Zero, okay, so that means zero, sitting 0 distance away from the origin, okay, so that's the lower. How far are we sweeping out to what's the outermost limit that R is gonna go up to?
Should
Yeah, so we're gonna go 2 units away from the origin, so let me mark out 1, 2, 1. Okay, and then before I start putting my pen down, let's see where I actually start sweeping and where I end sweeping, okay? Where do I start sweeping? Yeah, so we've rotated away from here 0 radians, okay? So the very first point I know it's gonna be sitting right there. Because that's a point that is 2 away. And we're sweeping all of the area out inside, and then we're starting at 0. How far do we rotate? Right, so 3 pi 4, so this would be pi 4, so that'd be 2 pi 4, so 3 pi 4 is gonna be the one that it's 45 degrees over like that. So it'll be something like that. Well, not really. Pretend like that's going through the 2, and this is a circle. And then it's ending somewhere in here, at 45 degrees. Okay, so we know that we started at theta is equal to 0, right? So we started at theta equals 0 radians, so we're ending here at theta equals 3 pi fourths. And the bottom is 0, and then the end is 2. Here's literally what's going on in this kind of a sweeping out of this rectangle. You're starting here, and it's sweeping all the way from R0 out to 2. Then we adjust. We're sweeping from 0 all the way out to 2. 0 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 out to 2. And this is going to continue with infinite level precision as we sweep out every single theta. And you'll notice that as I've drawn all of these lines, it's essentially just shading in the region. That's exactly what we're trying to represent. It's that particular region. So it's good to know visually how that's actually being drawn out. It's always starting at this lower limit, and then it's like as if you drew a line out to the furthest extent, and it's sweeping all of these things. That looks like a little seashell. Okay, so this is a polar rectangle. How are we feeling about drawing these? So if you saw, if you were given like an r theta, and then you're given bounds on r, you're given restrictions on theta, do you feel comfortable enough to actually draw that? Okay, you'll have a chance to practice that. There's a very specific lab question that's just targeted toward doing that one thing. So it's 24, okay. If there are no questions about that, let's now apply this to integrations. Thumbs up. If you really invest in understanding the polar coordinates and double integrals, cylindrical coordinates are going to be easy, because cylindrical coordinates basically says do polar and then have a regular z as if you were in Cartesian. So you're really learning 2 ideas right now in terms of understanding how it's swept out in this R2 by itself. But the only difference between this and the cylindrical is we're just add a z component so that we now can say it's a certain height off of after you spun it around a certain. Okay. I'm about to put some gobbledygook up here, so don't panic. I just have to put it up here because it's the math. So you got to know where it's coming from, but this is not necessarily what you'll be doing your computation with. So we're looking at this double integral of r for a surface fx y dA. And we already talked about this being the limit as delta approaches 0, this sum for k is 1 to n on the f of x sub k star and y sub k star, and then your change, you're like, basically remember that the delta AK, those like the bathroom tiles, is that you would add up over a certain region. Now, in this case, we're trying to convert to polar. So delta goes to 0, sure. We still have our k equals 1 to n, sure. But now in our function, in polar, what do we use to translate x? So x is what? Which trig? Yes, cosine. Cosine goes with x. So we have in r sub k star, cosine theta sub k star. And then for y, what's the y translation? Yes, fine. Theta sub k star. And then we still have our delta A. Okay, now this tile isn't going to look like the ones in the I4, like the bathrooms near the I4, because we're talking about polar rectangles. And so a formula for basically those polar, they're really just little arc length sectors. And so we have that, our little changes, little tiles per se, of delta A sub k is going to be the area of the outer sector minus the area of the inner sector. And when you sketch that out, and from geometry, we have 1/2 r sub k star plus delta r over 2, all of that squared times delta theta. And then we now subtract the area of the inner sector, which is going to be 1/2 RK star minus instead of plus the change in R over 2 squared, and then delta theta. So that once you simplify, you just end up with a very nice R sub k star times delta R delta theta. So when we plug this back in, we're actually going to have that the double integral for R or fx y a is going to be the limit as delta goes to 0 for the sum k equals 1 and then the function polar again x when you translate it over to polar is going to be what? R cosine, yes. So it'll be R sub k star cosine theta sub k star, and then the y is going to go to what? Yes, R sine theta. Good. So k star sine theta sub k star, and then now instead of just a regular rectangular tile essentially of our little changes in the area, we have polar rectangle changes in area, which is the RK star delta R delta theta. R sub k star delta R delta theta. This is not what you're going to be doing in problems, not on homework, not on the exam, but you need to see where it comes from. It's a very Riemannian idea all the way through. What you'll realistically be using and what we're gonna have, we're gonna talk about this and memorize this, is what I'm going to write on the board next, okay? So if you're wondering why there's all these random sub k's and stars, it's basically a nod back to when you construct the Riemann sums. And we're doing the same exact thing where we're arbitrary taking because ultimately the delta is going to 0. So it doesn't actually matter which point we take inside of each of those. Let's see. Go to erase.
No.
Okay. Give me a thumbs up when you're ready to go. I wasn't able to figure out how to draw on my notes, but the textbook actually has a nice like multicolor kind of like way to illustrate this. That would be impossible to do because they have to like shade it for texture. So use the textbook. It's actually really, really visually pretty to look at the way that this comes about. So there are limitations to only using Blackboard, but this is good enough for today. You know what I very firmly believe, especially as somebody who struggled a lot in high school mathematics. Leave nobody behind. So, never, I'm not afraid of awkward silence. Especially because it's always an awkward silence that most of the math work gets done anyway. Because in that wonderful few minutes, you had a cross the chance to kind of marinate on how beautiful that is. It's very satisfying. People did a lot of work to be able to say stuff like this. That's why I tell you guys to add a math double major, because you can start to see how deep it goes. I mean, you gotta define addition. It's not how that. How many of you are doing the math minor by chance? So you're gonna take either higher algebra or real analysis, which I would recommend taking both if you can. But anyways, here's what we're actually going to use. Okay, so it's that. Well, when I say actually going to use, we're technically using everything that we just wrote down, but we're using a theorem that was proven so that all of that math that we wrote down is going on in the background. It's kind of just like how all the bits and stuff are firing in a laptop when you're just using the surface level controls, right? So F, we need a continuous function because if there's a hole, you can't go underneath it. So let F be continuous on the region R in the XY plane. So we're still looking down on the same XY plane, and that's nothing changed here. However, we can change the way we express it. So express in now polar coordinates. In polar coordinates. And so the way we do that is we say R. And the reason I'm repeating this form over and over and over again is because the more you see it, the higher the chance that you'll actually recognize it. Okay, so R theta such that, and then we're restricting R between 0 to A, R, B. And then what are we restricting theta by? Start with some alpha. Alpha to beta, right, good. And then what's the one condition we don't want to double count stuff? What do we do? Very good. Okay. So if we have this setup, then we can say two things. The first thing we can say is F is integrable. That's a big deal. That means that integrals are even possible. Okay, that we can even do a double integral using the system over our region R. And now here's the formula you're going to want to double star, highlight, memorize, put on your toothbrush. So every time you brush your teeth, you see it in the morning. The double integral of R, if it's given in Cartesian f, x, y, a, to convert it to polar, the way we're going to do it is we first describe the region using the polar coordinate system, and then we always do the theta class. So it'll be alpha to beta on the outside. And on the inside, we have our a to b. Now we're going to, everywhere there was an x, we're going to put it, what are we going to put in for x? R cosine theta. And what are we going to put in for y's? Okay, good. And then now, remember, it's not just dr d theta. When we did that polar rectangle, there's a hanging on r thing. This is going to be the most easy thing to forget. It's dr. You actually add that in. So regardless of what you actually substitute, at the very end of it, you slap on an r multiplied by everything. R d theta. Okay? So here's what I want you to do. So for polar, dA is r dr d theta. For polar, what's dA? For polar, what is dA?
R d theta.
Convince me you've been paying attention. In polar, dA is
R d
okay. So then if we're in polar coordinates, dA is. Okay, great. What is dA in polar? What is dA in Cartesian? Good. Or dx dy, it doesn't matter. In polar, what is dA? In polar, what is dA? You happen to be in polar coordinates. What is dA? Okay, so now that's your point of exhaustion of having to repeat that. Now you'll know how exhausted I am when we get to the exam and you forget the R and the R, you already say that, okay? So if you happen to be doing a double integral and it so happens to ask you to use polar, what is the A? You know, there's two R's, D's, and P's. Already did it. I like to think of it as already did it all the time. The fact that I still remembered that when I was making my lecture notes without using the textbook is just scarred my brain with already did it. There's another one that we'll do for the spherical coordinates as well. But, okay, let's actually do a couple then. Now, if you happen to be in polar coordinates and you do a double integral, what is the A? Good. Good. Yeah. Guess what I'm gonna ask you if I run into you on the sidewalk?
We're just gonna say DA.
Well, no, but dA is not precise enough because if I said Cartesian dA, what would Cartesian dA be? Or dx, right? But if so I'd have to say polar dA, then that's.
You start to say polar.
Volume, okay, so let's find the volume of the solid bounded by z is equal to 9 minus x squared minus y squared and the xy plane. Step one, let's actually figure out what this is. Was there a question? Yes.
So the original equation, R, or we talk around theta, R, R.
What's gonna end up happening is the way that you always integrate it, you'll always want to do the r's first. So yeah, it'll almost always integrate in the order of r dr theta. In theory, it's possible if you really wanted to do that, but the way you have to substitute is. Yeah, no, just do it, because the thing is, those thetas are coming inside of trig functions. So then you would be choosing to trig and anti-differentiate and substitute instead of polynomial power rules, which are always going to be easier, especially with the numbers that you plug in. So it's more of a, people tried it and they realized, yeah, this is just horrible. I mean, you could choose to cut the grass with your scissors, but I mean, just because you can do it doesn't mean you should, nor is it really fun or enjoyable. So yes, r dr theta is great because that establishes also the order that you'll always pretty much be doing those integrals. So you don't have to question yourself, like, which one should I do? That's how it's gonna go.
You're gonna add that to the test.
Which one? Just r dr theta?
Yeah.
Well, I'm trying to remember, you actually have to do, yeah, r dr theta will show up, I think, because it's important. I mean, it's an entire chapter for just double and triple integrals, yeah. So, do you guys know what this is, quadratic surface?
Radius.
Okay, well, so pretend like the y is not there, what would that be if I didn't have that? Okay, what is it, going up or down? What if I made x constant, that's gone? So maybe if there's two parabolas on the axes, this is just a paraboloid, right? And the paraboloid is opening which direction? That's pretty good because we need to trap an area under like basically this cup with the xy plane. If you're trying to catch like a spider or like a cockroach or something. So we're gonna see some absolutely mad art skills here.
You're right, I am.
Dang, that was bad. Wait, hold on. I practiced this like in group advisement and I still can't get it. Oh, that's good. Here's the origin, and then here's the x-axis coming out. Here's the y-axis coming out. There's the z-axis coming out. And then so that we can really feel this spatially, going out the other directions. would be- Nice. Okay, so this is our surface and we gotta figure out what's going on. So when we're notice that, do you see what the region is we're under? What shape is that region in the XY plane that we're gonna be integrating?
Circle.
Circle. Now we can figure out exactly what kind of circle through this information. What is the value of Z on the XY plane? Yeah, so let's throw in 0. 0 is equal to 9 minus x squared, which is y squared. And as some of you already kind of noticed the general pattern here, we have a region that is a circle with radius what? Right, so this edge right here is 3. This edge right here is 3. How tall is this? Yes, 9. Because the tallest point is happening at the origin, and the origin is when x and y are what? Yeah, so what's 9 minus 0 minus 0? There you go. So with downturning paraboloid, that's kind of how you want to do that. Okay, so now that we know what the scenario actually is, this is what we're interested in. So let's take a look at this on a top-down view so we can set up our polar stuff, right? Because do you want to use a Cartesian description of that inner region of a circular set? No, you could, but now you're taking integrals where you're substituting square root functions of something minus something squared, which is a very high chance of being impossible with the way that rectangular rules work. Or just, you could use 10U substitutions and eventually kill it apart. So we could use polar. We're looking at this from a top-down view now. Here's my X, here's my Y, and here's my top-down view. And this is 3. This is 3. So looking at it from this way, this cup would actually be coming out to here, right? So it'd be like 9 units right about here, and then it would come down. So we know how to sweep this region out. So if we're starting at the origin, right? We're trying to include all these circular points. I'm not trying to cut ahead and only sweep out some of it. I'm trying to sweep out from 0 all the way out to a distance of what? So I'm going to 0, sweeping out a distance of what? 0 distance of what? 0 distance of what? Huh, is that the same for an entire circle? Yeah, okay. So when I set up this polar the polar rectangle of our theta, then what is going to be the lower bound for R? What's going to be the upper bound for R? 0. There you go. 0 less than equal to R less than equal to 3. And in case that's not visually clear, we start at 0, we sweep out to what? Start at 0, sweep out to what? 0, sweep out to what? We could record like a SNL like rap track. Okay, and then now we started sweeping out at 0, and then we are sweeping all the way around. What is my? Yes, the entire pie. So 0 less than equal to theta and equal to pi. Rocket science?
Yes.
Okay. Technically, yeah, this is used in rocket science, not ironically. Like for noses of ships and stuff, yeah. But is it visually intuitive? Because once you get this visual intuition, you can really set these up. If this was an ellipse, okay, well, you wouldn't be able to just do it as easy as like 0 to 3, 0 to 3, 0 to 3. But you would take the polar equation and know that the R of whatever something theta is going to be what that is. So that is going to give you the bounds. And so when I take a look and I need to transform my equation. So right now in a rectangular, I have Z is equal to 9 minus x squared minus y squared. However, when I integrate this in polar, what's the x gonna turn into? So all x's are what? Are cosine thetas, and all y's are what?
R sine theta.
Right. So we're gonna use it to transform the description of the surface with r and theta. So Z is 9 minus, what was x? We put r cosine theta all in parentheses, square that, minus, and then what's y?
R sine theta.
Theta, all that squared. What's this is gonna happen is we're gonna get 9 minus r squared cosine squared theta minus r squared sine squared theta. Funny, cosine squared. We have minus and minus. So we can pull out 9 minus r squared times, so the minus r squared is on both. Cosine squared theta. Plus sine squared theta. What do we know that to be? Yes, that's our Pythagorean identity. So we have 9 minus r squared times 1. That is a really easy integrand. Compare that with doing power rules on this and then substituting into your antiderivative the square root of, because you have to right? Because you have to do root of 9 minus x squared and then negative root 9 minus x squared. And that's not a good time. So, because now, as with the formula, what's my alpha? What's my beta? 0, 2, 5. What's my A? What's my B?
3,
What's my function translated into polar?
9 minus r squared.
Okay, so in polar, what is the A? In polar, my dA is what? Do you see now what I mean by how easy this is to forget? Okay, so are we gonna forget it? Good. When we re-express, get 0 to 5, 0 to 3 of 9r minus r cubed. You already did it. Please, for the love that is all that is holy, show these as separate steps. Okay, because what's gonna happen is if you account for your r, but then you remember in polar dA is r dr theta, you might accidentally give yourself 2 r's. Now you've overcompensated for what's going on.
Aren't you supposed to divide by 3? R cubed over 3?
You just multiplied the R.
I just multiplied the rn, so 9 times r and then minus r squared times r. Yeah, because the r is quite literally just like the variable in the integrand. So this becomes the integrand. Yeah. This is just a double integral on a rectangular region if you really think about it. So you know how to do those. I'm not going to waste your time with arithmetic.
Do you forget the RDR, like the, no, what?
No,
What's the difference between these two?
Oh, I got you.
Yeah. So, but do these as separate steps, because see how easy it is already to kind of confuse which one is, wait, did I already put the RDR in or is it? Yeah, so keep those steps separate. Show what the translated surface would be, then give RDR theta, and then combine the RN.
So there wasn't a left, for example, with the three would be replaced by the long side, the long, part of the ellipse, for example.
Well, the way you would describe the polar region would be different, essentially. So you would have, instead of it just being 3, because right now this is like 3 cosine theta and then 3 sine theta for the lines. So you would adjust. So if it was like wider here, so maybe it was like up to 5 and only 3 here, then it would be 5 cosine theta and then 3. But don't worry about that as much, because that really, the reason why we have this is because of a surface. So your region is going to be dependent on what kind of surface you're using. In most cases, it's circular. Yeah. Because you're intersecting cones and stuff. Yeah.
So those graphs, you have to know them off by heart. Those z equals to 9 minus x squared minus y squared. You already know the region. You have to know the graphs by heart. The z equals,
Right here.
yeah,
Do you need to know
you
V?
have to know the graphs by heart, isn't like to be able to compute it. Be able to draw the graph. The z equals to 9 minus x squared minus y squared on top.
So like
The function on top.
this is the
Yeah,
function.
do you need to know the graph by heart, like how to draw it off and stuff?
Oh, I mean, I don't have all of them memorized by heart. What I do know how to do is I know how to figure out what it looks like from click. And my best strategy is to cover up other variables and see what is familiar. So I don't, because I've been teaching this for so long, I can look at that and I can tell you exactly what this is. But when I first started, I couldn't tell you what this was. So I would say, okay, well, interesting. Let's just get rid of the line. What does that look like? And then break it down clue by clue, because then I say, well, what's the only possible shape really if I have parabolas on the x plane and the y plane? And so it's going to be parabola going down. Say this was like the cone equation or something like that. Well, then I would be, when I remove one of the variables and what it's going to look like if I were to just graph it like that particular slice, I think, interesting. So if that gets rotated around, what shape am I going to get? That's where it just really comes down to your familiarity with the either equation forms or ability to piece together from your algebra stuff what's going on. So I wish there was a formula for it. I really do. It would have made my life easier 2 years ago. But it really comes down to just familiarity. And, okay, let's do. It's 52, so here's what's gonna happen. I'm going to show you, I'm gonna give you a practice problem. Like you'll write down, but we won't do it in class. Actually, you already have the lab question, so if you're gonna do one, do the lab question. I'll show you one more thing we can do with these regions. In the same way that we had rectangular region for double integral, we could also make it general. So instead of necessarily binding it by a very specific rectangle, you can have the bottom be an actual function with respect to something. You could have the top be an actual function, or even if you switched it over to x and y. So what you can do is sometimes that r, you might have noticed we fixed the r and it was unchanging, it was constant as you swept around. That's not always the case. Sometimes you'll have an r squiggling as you're going around with respect to some sort of a polar function. So yes, we can accommodate for that. The intuition is exactly the same though. So that's why when I was showing you start at 0, go out to 3, 0, go out to 3, 0, go out to 3. If you start thinking about that with just general functions, start at the lesser function, go out to the greater function, start at the lesser function, go out to the greater function. So I'll draw an example of what this kind of looks like. So for a general region, let's make this nice and big here. So here's our reference where it's technically in the xy plane. And if I chose some sort of a theta starting at some alpha, and then maybe let's do a more patient one. So let's do, we're not sweeping out as far. Beta is a little bit closer to alpha. Okay, but instead of just fixing like a constant distance for the lower bound, what if I actually had some sort of a function where this function is giving a r, it's giving a distance away from the origin determined by some function of theta. So it's changing. So depending on where I've swept out in theta, the r value, the distance away from the origin will spit out a different value. Okay, and if we're gonna do that here, we can also have one down of the top, so I can maybe do something kind of like that. So then we're containing. I mean, imagine trying to do this in Cartesian coordinates. Your computer would vomit. Even Wolfram probably wouldn't even want to do this. This would be some other. Again, it's an r value. That's the important part. These are still r values. It's just now being described as something that's changing depending on how far or where you swept out. Okay, which one's greater, G or H? Right, which one is less? Okay, so just as we would start at the lower and go out to the way we sweep out this region R, start at the lesser, go out to the greater, start at the lesser, go out to the greater, start at the lesser, go out to the greater, start at the lesser, go out to the greater. It's the same idea. So just because we change this to being functions instead of constants, technically a constant is a type of function. It's the one that you just fix it regardless of where you're at with theta. So now we're allowing for the chances. So you might have different circles or lemniscates case. Or if you remember your polar functions from Calc 2, you could have like those flower petals and then taking various regions in between flower petals. That allows you to do way more crazy things that Cartesian brains just can't even fathom doing because it would be so terrible. So all we got to do is make one slight adjustment to our region. We can no longer call it a polar rectangle because that's not a polar rectangle, but we can still describe what's going on in our theta with a small adjustment. What's going to be the parameters for our radius now?
0 less than u theta, what is its possibility?
Okay. And then what is the, did we change anything with the way we sweep out with theta? No, we don't. That's the nice part. So theta stays the same. It's going to be alpha less than equal to theta less than equal to beta, with that condition still applying, where beta minus alpha less than equal to 2 pi. And so when we apply that to setting up a double integral formula, we have the double integral. I'm gonna run out of space. We have the double integral. For this particular region. If it was originally given in fxy, which it wouldn't be, because that would just be. Horrors beyond horrors, and this is now. What is gonna be the outer integral? Well, alpha, beta, and then the inner integral. What's the integrand going to be? Okay, more, the way I mean is, x is going to become what? And the y is gonna become, and then in polar, what is the a? Ooh, people have already begun to forget. In polar, what is the a? Okay, and if you so happen to be using Cartesian. You have dA is what? But we're in polar, so dA is gonna be. Alright.